Hi, everyone. So to build on the last lecture, now that we have a way to figure out the distances to stars by using parallax, how can that help us learn about brightness? And when you talk about brightness, it's important to make a distinction between how bright a star looks from here on Earth and how truly bright it is, how luminous it is, how much light the star is giving off. Uh, Why is there a difference? Well, because how bright a star looks also depends on its distance. If you look at a star tonight and it looks very bright, well, why does that star look bright? Is it because that star is very close to us? Or is it because the star is giving off lots more light? If you don't know what the distance to that star is, then you really can't answer that question. Conversely, if you look at a star from here on Earth and that star looks very faint, well, why is that? Does that star look faint because it's far away? Or is it because the star is just not emitting very much light? Again, we need to figure out the distance to get to the real intrinsic brightness of the star, right? The same is true for stars as it is for light bulbs. The farther away the light source is from you, the fainter it's going to look. But we can't just be content to say how bright stars appear from here on Earth. We want to know real properties of stars. We want to know what the intrinsic properties of stars are, like brightness. And so one of the ways to measure the intrinsic brightness, the real actual brightness of a star, is what's called luminosity. Luminosity is a measure of how much light is the star actually emitting. But we can't just look at a star and automatically know how much light it's emitting because, well, if we don't know what the distance is. So we can figure out how bright the star is. We can figure out the absolute brightness of the star if we have the apparent brightness, how bright the star looks from here on Earth, and the distance. If we know how far away the star is, then we can get to the answer of, well, how much light must that star be emitting if it looks as bright as it does here on Earth from as far away as it is? And so that's why measuring the distance to stars is such a constant problem in astronomy, right? If you don't know how far away objects are, then all you're doing is saying what they look like from here on Earth, but you can't get to the real physical properties of the stars. Once you've got the distance, though, by parallax or by some other means, then you are off to the races. Then you can start figuring out things like luminosity and mass and size and age and all of the other things that you might want to know about stars. So distance is the first step. The second step is what we're doing right now, luminosity. Let me explain what I just said a little more clearly. The luminosity of a star, or I'm calling it the absolute brightness, right? Absolute brightness as in it's not how bright the star appears, it's the real brightness, it's the intrinsic brightness, is measured in terms of luminosity, okay? Luminosity means something very specific. Luminosity is the total amount of energy in light that star radiates per second. So when a star gives off light, I've got my silly little animation here. When a star gives off light, that light radiates away from the star in all directions. And so the luminosity is the total energy from all the light that star gives off, radiating in all directions every second. That's the goal, right? We want to get to the luminosity because if we know the luminosity, then we know something real about the star. We know how much energy it emits per second, right? Now we're really getting at solving the mysteries of what are stars. How do they work? Let's take a second and talk about SI units. Remember from whenever the last time you had a science class is, right? SI units are the basic units for measuring scientific quantities. Right? It's the metric system. The SI units are in the metric system, but specifically it's the metric system for measuring properties of objects in nature. And, SI units are used in physics, chemistry, biology, and astronomy. The SI unit for energy is what's called the joule. So joules are units of measuring energy. And so you could talk about the luminosity of a star in terms of joules per second. Right? Because the luminosity is the energy emitted per second. So luminosity is in joules per second, but luminosity, or I should say, energy per second, joules per second, have been shortened to just a unit called the watt. So luminosity is measured in watts. This may sound familiar. You've probably measured electronic devices in watts before, right? You go shopping for a light bulb, it's a 60-watt light bulb or a 100-watt light bulb. You look at a microwave, and you're shopping for a microwave, and that microwave has a wattage of 1,000 watts or 2,000 watts. Right? What does that mean? That wattage is essentially a measure of how much energy that object uses up per second. Right? A 100-watt light bulb has a luminosity of 100 watts. It gives off 100 joules of light energy per second. The same is true of a star. Right? A star's luminosity is how much energy it gives off, how much light energy it gives off per second. If you're talking about this in SI units, that's measured in watts. But that's not what we see here on Earth. Right? What we see here on Earth is the starlight that hits the Earth. And so if the Earth is, let's say, off in this direction, right, all of this light that's shining away from us, well, we don't see that. As that starlight, as that luminosity travels away from the star, that light is being spread out across space. That light is being spread out over larger and larger spheres. And so the light that we see is a measure of the light that is spread out. Right? If you're, let's say this square here is your eyeball or your telescope or the surface of the planet, right? The light that hits your telescope, let's say, is the light that heads in this direction. If we move to be 2 astronomical units away, and your telescope is, let's say, this square right here, then that same amount of sunlight is now being spread out over a larger surface area. And therefore, the energy that hits your telescope is going to be lessened. How much energy hits a unit of area per second is what's called flux. So let's sort of zoom in and think about flux for a second, right? Because what you see when we see the brightness of a star, what we're seeing is the flux of light, right? If this circle here is either the mirror of your telescope or your eyeball, right? If 3 rays of light go in your eye, well, that's less light hitting your eye per second. The star is not going to look as bright because there's less flux of light going into your eyeball in a second. If now like 6 rays of light go into your eyeball, well, that's more flux going through into your eye in a second. The star's going to look brighter. The flux is more intense. So flux is a measure of the intensity of light. It's a measure of how much energy, how much of that star's luminosity hits a surface area, a unit of surface area in a second. And so calculating the flux is actually fairly easy, right? You just need to take all the luminosity from the star, divide by what's the full surface area over which that light is being spread, and then you have a measure of the luminosity per area. So as this starlight travels away from the star, that light is being spread out over a larger and larger spherical surface. And therefore, the energy that hits 1 square meter or 1 unit of area is going to be getting the intensity of light, the flux of light that hits a unit of area gets less and less and less because the same amount of energy, the same amount of luminosity is just getting spread out. It's being spread thinner and thinner and thinner. Now, for our purposes here, this isn't that difficult to calculate because the light is being spread out over a spherical surface, and the formula for the surface area of a sphere is 4 pi times the radius squared, right? The surface area of a sphere is always 4 pi times the radius squared. Well, in this case, what is the radius of this sphere? The radius of the sphere, let's say your telescope is right here, the radius of this sphere is the distance from you to the star. So the surface area of this sphere is 4 pi times the distance squared. You take the luminosity of the star, divide by the area over which it's spread, and you've got the flux in how much of that energy hits a square meter of area in a second. The more energy hits a given square meter of area in a second, the brighter the star is going to appear. So flux is a measure of apparent brightness, like we saw here, right? This star would appear less bright. This star would appear more bright, right? The flux doesn't tell us anything about the luminosity. The flux just tells us how much light am I getting from the star in my eye or on my telescope in a second, right? So flux is a measure of apparent brightness, but the flux that we get from a star depends on luminosity and distance, right? If you look at a bright star, why does that star look bright, right? That star looks bright because there's a lot of flux of light going in your eye, but that star might give you a lot of flux either because the star is really bright, it has a high luminosity, it's giving off a lot of light per second, or maybe it's just because the star is close to you, and therefore the light is not being spread out over as large of a surface, or both. Maybe it's both. Maybe the star looks really bright because it's giving off a lot of light and it's very close to you. Could be both. Flux, if we think about our units of measurement now, flux is usually measured in units of watts per square meter, right? Because luminosity is measured in watts, and the SI unit for distance is meters. So then you take the meters squared. That's the unit for surface area. So then the flux is the flux is measured in watts per square meter. In other words, I'm going to slow down. Let me slow down because this is getting a little dense, right? Flux is measured in watts per square meter. Why? Because flux is a measure of how much energy in a second, that's the watts, right? How much energy in a second hits 1 square meter of surface area. Right, whether it's this square meter or that square meter or that square meter. How much light hits that in a second? That's your flux. And that tells you how bright the star, or that explains how bright the star appears. Okay. So this is something we measure directly, right? You look at a star. How bright does the star look? That tells you the flux. We can figure out the distance usually by means of parallax. So we can get the luminosity. And like I said a minute ago, that's the goal. Figuring out how bright the star is really. What's the actual brightness? That's the goal. So the homework and the lab work gives you some formulas to relate flux and luminosity. It does it pretty quickly. So I wanted to slow down and break down what is the relationship between luminosity, flux, parallax, distance, all these things we've been talking about. Okay, so this is the equation we just had, right? The flux in watts per square meter equals the luminosity in watts divided by 4 pi times the distance squared, and the distance again is going to be in meters because we're using basic SI units here, basic physics units. Let's rearrange this algebra and solve for the luminosity, right? Because that's what we want to find out. We want to find out what's the real luminosity of this star. So the luminosity is just 4 pi distance squared times flux. Okay. we know, or we can figure out what the distance is because the distance is 1 over the parallax. Except, remember that when we take 1 over the parallax angle, that gives us the distance in parsecs. Right? For this equation, we want the distance in meters. So we get the distance in parsecs from parallax. We know that 1 parsec is 3.086 times 10 to the 16th meters. So then if we just take, we can get the distance in meters if we take 1 over p, which is the distance in parsecs, multiply by the number of meters per parsec, and that'll give us the distance in meters. All right, it sounds like it's getting complicated, but we're going to simplify it here in just a minute, right? Because now we've got this expression, this formula gives us the distance to that star in meters. That's why this number is so huge, right? 3 times 10 to the 16th meters is 1 parsec. Stars are really far away in meters. That's why we usually don't measure the distance in meters. But in this case, we have to, right? In this case, we take our expression for distance in meters, plug it in here because we need the distance in meters for this formula. And now let's take this equation, plug it in here, and simplify. Okay? This looks ugly, but we're going to simplify it here in a second. Right? Now the luminosity is 4 pi. The 4 pi is right there. Right? Times the distance squared. The distance squared is going to be the 3 times 10 to the 16th squared divided by parallax squared times the flux. All right, so all I've done is take our last expression for distance and plug it in there, and it turns into this big nonsense divided by parallax squared. This will give us the luminosity of the star in watts. Now, I said before, right? A light bulb has a luminosity of 100 watts. Your microwave oven has a luminosity of, or a wattage of, 1 or 2,000 watts. Think about the sun, right? The luminosity of the sun, if you measure it in watts, what do you think the wattage of the sun is? It's huge, right? That's why we're taking this big number, you square it, that's going to be an absolutely colossal number. Because the luminosity of a star in watts is a huge number. 1 solar luminosity. So we're gonna invent a new unit, much like we've been doing all semester. We're gonna invent a unit, the solar luminosity, where 1 solar luminosity is the luminosity of the sun. And most of the time I will write solar luminosities as L sun. The homework sometimes just symbolizes it L sub s, so I'll give you both of those there. Right? 1 solar luminosity is 3.8 times 10 to the 26th watts. So that's a big unit. All right? Why don't we just talk about luminosity in solar luminosities? That would make the numbers much more reasonable. Measuring luminosity in watts, we're going to be juggling these giant numbers in scientific notation. So let's not do that. Let's convert our answer. This equation gives us the luminosity in watts. If we just divide by the number of watts in 1 solar luminosity, then that will give us the luminosity of any star measured in solar luminosities. And that number, the luminosity of a star in solar luminosities, is going to be a much smaller number, and that's going to be a much more reasonable number. So, what is all this business here? Right? We got 4, the same 4 we had here. Right? 4 times this big number, the number of meters in a parsec squared, divided by the number of watts in a solar luminosity. All of these numbers are just constants. Right? These are not variables. These are just constants. So let's just do the math. Let's take this times that squared divided by this. All of this number here simplifies to equal 9.94 times 10 to the 6. All right? 9.94 times 10 to the 6. Okay, it's still a big number, but it's not huge. It's not so unwieldy. The rest of this just follow through. Pi times the flux divided by parallax squared. That's where this equation comes from in the homework and in the lab work. Right? This equation didn't just pop out of nowhere. I'm not just handing it to you and saying, hey, trust me. This equation came from all of the steps that we did before, based on all the things that we already know. And so this equation here is it doesn't look that very simple. It's a little awkward. It's a little bit of an awkward expression, but this is the simplified version where we plug the flux in watts per square meter, which is the unit we use. You plug the parallax in arc seconds. You plug the parallax in arc seconds, like we always do, and you simplify this expression, and that gives you the luminosity of any star in solar luminosities. Now we've figured out a second major thing about a star. We figured out the distance before. Now we can figure out the luminosity. So I would recommend, I'm going to pop over to my spreadsheet here. All right. Let me make this so that you can actually see it. Okay. If you're setting up your spreadsheet, all right, you could do this in different ways, but I like to keep my spreadsheet organized where the measurements that I'm making directly are over here, and then all the conclusions are over here. So basically, these are my inputs, these are my outputs. All right, what's my first measurement? Well, parallax is my first measurement. Let's say the parallax is half of an arc second. All right, this is the value. I'm just making a note for myself right there to record the units. That way I remind myself what the units for parallax are. All right, once I've got the parallax, I can calculate the distance. What is the distance? Distance is 1 over the parallax angle. And then if I hit enter, it says, okay, that star is a distance of 2 to what? This equation, if I do 1 divided by parallax, that gives me the distance in parsecs. So I make a note for myself. Yes, that's the distance in parsecs. All right. What's the second measurement that I can measure? I can measure flux. You look at a star, how much energy do I get from that star per square meter per second? That's the flux. Let's say 1,000. No. Typically the flux of stars is very low. So I'm going to say 1 times 10 to the negative 7. All right. If the flux was 1 times 10 to the negative 7th watts per square meter. Okay. What's the luminosity? Nope. There we go. This is where this equation can come in very handy, right? Because these are my two inputs. These are my two direct measurements, flux and parallax. I just have it crunch this number, and that'll give me the luminosity. So the luminosity of that star equals 9.94 times 10 to the 6th power times pi, 3.14159, times, I'll give some a little more room here, times, I don't want to totally go off screen here. Well, okay. 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 So 9.94 times 10 to the 6 times pi times the flux, which is that cell right there. Right? So far, so good. 9.94 times 10 to the 6 times pi times the flux divided by the parallax squared. So I want to take all of this. I'm going to multiply these three things together. 9.94 times 10 to the 6, that constant, times pi, times the flux. And then I'm going to divide by the parallax squared. Right? I'm multiplying these three things together on top. I'm dividing by the parallax squared on the bottom. I hit enter. Okay, that star has a luminosity of 12.5. What are my units for luminosity? Well, this equation is explicitly meant to give us, this equation is designed to give us the luminosity in solar luminosities. Okay, now I've got my spreadsheet where all I have to do is put in new, if I'm looking at a different star, I measure its parallax, I measure its luminosity, let's say 4 times 10 to the negative 8. All right, I put in my two measurements. The spreadsheet automatically updates to say the star is this far away and it's this bright. All right, problem solved. On to the next thing. Save your work so that when we add a third equation, we can add a third line to our spreadsheet. All right, I hope this clarifies and explains some things. This is some dense stuff, right? This is a lot to grasp the first time. So hopefully, after you've gotten a little bit of practice with it, it won't be quite so foreign. All right. Have a good day, everybody.